Good morning. My name is Marcin Moczulski. I'm working in C application support EMEI team. Today, I have the pleasure to tell you about differences between isoelectric focusing and capillary zone electrophoresis techniques and how they both enable charge profiling of proteins. Outline of this presentation is short introduction. Tells you how capillary electrophoresis can be useful for charge heterogeneity analysis, and more about two techniques, high-resolution capillary isoelectric focusing and high-throughput capillary zone electrophoresis. And finally, short summary. What is a protein charge variant? Proteins are large biomolecules consisting of at least one or more long chains of amino acid residues. And some of them are common therapeutic type of drug, for example, monoclonal antibodies. A charge variant is an alteration of protein resulting post-translational modifications or chemical degradation, which modify final charge and affecting for isoelectric point of these proteins, leading to charge heterogeneity and can include or acidic or basic variants. This table shows typical modification which might affect to increase or basic or acidic character of proteins. For example, for basic, it happens by loses carboxylic or formation amine groups, and vice versa. Acidic variants can increase by formation carboxylic or loss the amine groups of proteins. Why protein charge heterogeneity is so important? It's because allows to measure post-translational modifications of proteins and provide stability determination, can identify and characterize clones, provides lot-to-lot consistency. Typical method used to determine charge variants are ion exchange chromatography and two techniques based on capillary electrophoresis, means capillary isoelectric focusing and capillary zone electrophoresis. For this moment, I would like to tell you more about high-resolution capillary isoelectric focusing method. What is isoelectric point? Proteins, peptides are part of switch-turning components, which charge depends on pH of environment where they are placed. That means they can have as well positively or negatively charged, depend on pH. However, if pH is quite suitable to obtain balance between carboxylic and amine groups, net charge value of these switch-turning components as the proteins will be zero. Capillary isoelectric focusing is a technique which allows to separate molecules based exactly on their isoelectric point. This is identical methodology based on gel electrophoresis, which is based on three steps: when we loading sample, focusing them, and finally, or we can imagine or do chemical mobilization. pH range of possibilities in separation depends on used ampholytes, also switch-turning components, which typically are used in wide range, commonly used between 3 to 10, or also they are available narrow ranges focusing for specific range of PI. Migration time of our analytes can be correlated with calibration plot of the PA value versus migration time of used protein or peptide markers. The most important is to understand capillary isoelectric focusing technique to be successful. This methodology using couple of phenomena allowing us to be successful with separation. One of these is mentioned before, switch-turning character proteins, where we can affect and allows to neutralize proteins during gradient formation. Gradient formation is allowed by isotachophoretic technique, where it's a very simple method where we trap mixture of our samples between two different type of buffers, leading and terminating electrolytes, which generate specific behaving of ions which replace each other to order from the highest to lowest protonation. In this technique, we're using only electrophoretic separation character. That means only charged molecules can move in the electric field. And finally, we use phenomenon also related with photonic components, where by different treatment of environment and titration, we can reduce, in this case, in this method, pH going below isoelectric point of each zones we determine during gradient determination. And because of that, protonated, finally, zones, including also our markers and proteins, can be easily moved through capillary. For these techniques, we use neutral capillaries, capillaries which are coated with hydrophilic layer, excluding accessibility to silica. Because of that, there is no chance to be faced with isoelectrofocusing, with electrosmotic flow impact for separation. Typically, neutral capillary used for these techniques are coated with linear polyacrylamide, but also polyvinyl alcohol coated capillaries can be used. Because specificity of the layer, we have some limitation for buffer use for these capillaries, and typically pH buffers which can be used for these capillaries is between 3 to 8. Also, capillaries are quite sensitive for higher currents and automatically for higher temperature obtained during separation. Hence, the maximum temperature obtained for this capillary is only 40 microamperes. However, capillaries for recovery can be rinsed with weak acids like acetic acid or hydrochloric acid as well. Mentioned separation based on electrophoresis, when there is no impact of electrosmotic flow, allowing to bidirectional process of separation charged molecules, where negatively charged molecules can easily move to positively charged anode, positively charged molecules move through capillary to negatively charged cathode. Neutral components cannot move in this mechanism. After gradient formation and a chemical mobilization, protonated zones can be easily moved through capillary, giving us possibility to monitor and see peaks, where first peaks separated are much more basic, the last peaks are much more acidic. However, still protonated, still positively charged. This technique is based on 3 steps. First, most critical, it's sample preparation when we mix separation gel, including or not urea, depends on optimized method per used samples. Ampholytes responsible for gradient determination. Anodic and cathodic stabilizer protects obtained gradient. P markers helping us to generate PI plot, and finally samples we're going to separate. Critical point is appropriate mixing of this whole solution, giving very homogeneous solution itself. And then during method, these samples are introduced into capillary by capillary filling completely with sample matrix. Next step is applying 2 different buffers conductivity solution. Very acidic, which is phosphoric acid, applied from anode side, and sodium hydroxide applied from cathode side. When we apply voltage, what happens with molecules, it's exactly isotachophoresis phenomenon, when molecules from each part of capillary move on through capillary to find the exact place depending on their protonation. In the same moment, still phosphoric hydronium cations and from opposite side hydroxyl anions coming from sodium hydroxide moving through capillary as well. So all components, ampholytes, stabilizers, peptide markers, as well proteins formating gradient, and in the same moment they are treated with hydronium and hydroxyl ions, which affect finally to obtain balance between the ionizable groups, and finally all components present in capillary will be neutralized. During focusing, what happens with part of ions coming from the cathodic part is when they passing through the detection window, which is permanently active, we can observe the signal as small peaks, or which is called cathodic peaks because coming from cathodic side. If we're meeting these peaks, that means this part of capillary wasn't well protected by cathodic stabilizers. More information you can find on this slide. Final effect of gradient determination is obtained gradient from the lowest to highest value of pi. Gradient is protected by two stabilizers. From anodic side, stabilizer is in imidodeacetic acid. From cathodic side, L-arginine solution. Both must be in optimized high concentration, which increase conductivity in these zones, and by this reducing local electric field for hydronium and hydroxyl ions coming through capillary, because still we provide the same voltage and separation process. By reducing movements of hydronium and hydroxyl ions, we can keep this gradient obtained during focusing constant. It's not movable for the moment. And there is a moment when imaging techniques make a stop, take a picture, and we see effect of final focusing. However, in SCIEX method, as of the focusing, we continue process when cathode light solution, sodium hydroxide, from cathodic side is replaced with acetic acid. And we continue process using a little bit higher voltage, maximum 30 kilovolts. This allows to introduce into capillary acetic acid ions, which is moving very, very fast. And by decreasing pH, we are able to protonate each created zones, starting from cathodic stabilizer, an arginine, then from the highest to lowest pi value gradient. And because of that, each protonated zone, when passing through the detection window, can generate signal. If we have real peptides or proteins which passing through these zones, we are observing this effect as a peaks on the electrophoregram. Historically, for mobilization, pressure was used. However, pressure increased molecular diffusion, which finally causing reducing resolution. Keeping only chemical mobilization, when we only titrate environment by using acetic acid, we are able to get really strictly high resolution separations. This slide, this slide shows an example and comparison of two techniques used in the past based on hemoglobin separations on capillary isoelectrofocusing method. Final effect of separation you can observe on this slide when you see two different traces. Blue one, absorptivity of separated proteins, and magenta one, profile of current obtained during this separation. As you see, current profile is not constant, it's not stable, and is changing dynamically during the whole, as well, first, in this case, 15-minute focusing process, and the rest, chemical mobilization process. Both helping us to monitor what's going on inside of capillary, so we can say that each single run is self-system suitability test, which tells us a lot if everything is fine with separation. When molecules, that means amphiolites, peptides, proteins, and stabilizers moving on through capillary to find the well position, current obtained the beginning is reduced, and by the end, obtain some kind of equilibrium. So if we elongate the process, we could see only flat baseline here. Of course, it doesn't make sense to provide this process. We stop them. And finally, we elute, means chemically mobilize each zones by introducing acetic acid ions into capillary, and by somehow chemical eluting each zones, we reduce extra ions which somehow reduce conductivity of solution. And we observing how conductivity is increasing when each next zones of PI gradient is moving out from capillary. By the end of separation, chemical mobilization step, what we can observe that current obtains some kind of equilibrium, because finally we have only gel with some urea residues, and well, it's nothing to be separated. The same we see by the end of absorptivity, small step visible here. First, cathodic peaks also tells us if in appropriate time all of them are separated. And finally, in chemical mobilization side, we observe PA markers, which are added to our mixture, and finally profile of our separated proteins. PA markers are helpful to create linear isoelectric point plot, and tells us about quality of linearity gradient we obtain during separation. Finally, we don't need them for final peak identification. So in the method allows us to exclude them from final integration, and we can be focused only to integrate our final peak profile, where first peaks are much more basic, middle range, main peaks, and the last group concerns acidic groups. We have also another tool in hands. Improving resolution means small aperture in the size of 200 micrometers. However, if we have very low concentrated samples, we can increase sensitivity using higher aperture. However, in this case, we reduce resolution. Protein concentration affect for eventual precipitation and aggregation means most of proteins have relatively low solubility in relatively high concentration close to the isoelectric point. And because of that, it might generate some challenges with separation. Nevertheless, isoelectrofocusing method can concentrate protein more than 100-fold. If we have a problem with eventual precipitation or aggregation, which has a causing for the final quality of separation, we can all reduce sample concentration, or we can use some protein solubilizer helper. In this case, we can use urea as a mild denaturant, which can disturb the non-covalent bonding that leads to protein aggregation and precipitation. Uses of urea allows us to use more concentrated samples. However, we have to remember that more urea presence allows from us to increase focusing step, means focusing time. This slide shows one of the experiments we made, and I have possibility to participate in this experiment as well, in master control, in master classes. We made many years ago in High Wycombe in UK. When we work with proteins which in relatively not so high concentration of urea still had tendency to precipitate or create some kind of aggregates. Increasing urea concentration, we were able to optimize method and obtain very nice and stable profile, allowing to determine appropriate isoelectric points of separated proteins. Another critical point of this method is appropriate capillary cleaning, where we have an established step in the method where cleaning is forced by use pure formamide. Alternatively, relatively middle range, high concentration of urea, 4.3 molar, can be used for capillary cleaning. Missing this step or bad quality of used solutions can affect or loses reproducibility of separation. There's no necessary to optimize concentration of used solution like sodium hydroxide, phosphoric acid, and acetic acid, because current method provided allows to get very high reproducibility. comparing to the previous method used in the past. Also, we have enhanced arginine cathodic stabilizer, which help us to be focused for more constant and reproducible separations, as well can be used to modify method to be focused for a more neutral and acidic range by reducing concentration of arginine. However, typical arginine concentration in the standard methods is approximately 40-42 millimoles in final concentration. By reducing of arginine concentration, we lose a little bit linearity. So high linearity in the whole range between 3 to 10 pi, we can obtain only in relatively high concentration of arginine, starting from 40 to 50 millimoles. We can modify also temperature if it's needed to accelerate separation, knowing that increasing temperature, we increase mobility of separated molecules. Method is optimized for 20 Celsius degrees. So if we decrease, automatically we reduce efficiency of separation. By increasing, we can increase. By increasing temperature, we are affecting to increase temperature inside of capillary, which by the consequence, for long term, might reduce shelf life of capillary. Another thing we have to remember is the presence of salts, which might coming together with sample matrix. And there is a quite critical point to reduce salt concentration by desalting if it's necessary. It's because salt presence can affect for appropriate gradient determination, stability, and finally for final conductivity obtained during even focusing and chemical mobilization. Too high conductivity increased temperature inside, which negatively impact for capillary coating. Hence, again, to be stable with gradient determination, to be successful to elongate shelf life of a capillary, the best is to reduce salts present from the sample matrix we mix with master mix during sample preparation. Robustness of the method was done by intercompany collaboration and presented in the article in 2011. Alternatively, method to isoelectrofocusing is capillary zone electrophoresis. Very simple method, also allowing to monitor charge heterogeneity, where mechanism is very robust and reliable for daily routine applications. In this method, you can use barfuse silica capillary without afraidness of eventual impact of electrosmotic flow. However, also neutral capillaries can be used. Separation is based on hydrodynamically, it's based on mobility differentials, means charge to hydrodynamically size ratio. Detection designed for 214, allowing to get high sensitivity. Method based on elevated concentration of epsilon aminocaproic acid and dynamic coating caused by the triethylenoltetramine suppress interaction between annulates and capillary wall. How molecules are separated? Mechanism is very simple. We see differentials of mobility, charge to size ratio of separated products. When the first peak observed, we observing means representing basic variants, we observing the largest charge to mass ratio. Then we observing basic steel variants, which reduced ratio between charge and size. Then we have a middle range, and finally we have we observing separation of smaller charge to mass ratio molecules. However, what is important in this application, all separated peaks represent positively charged proteins. Methods can be altered, can be modified by parameters like pH, viscosity of separation solvent, ionic strength, applied voltage, and finally buffer composition. However, for general biopharma purpose, we started a couple of years ago with commercial kit designed exactly for charge heterogeneity determination by capillary zone electrophoresis. Kits include protein test mix, helping us to see consistency of the kit, allowing to get high resolution C method for charge variants in the native state. It's or no or little preparation method development, very simple sample preparation, and giving high analytic throughput than cIEF or ionic exchange chromatography. And also for this method, we can use pre-built, pre-assembled cartridge with total length 30 centimeters capillary as a starting point. Using shorter capillary total length and this kit, we are able to get very fast separation. Of course, fastness of separation depends on the final isoelectric point of separated proteins, means much more basic proteins are separated much faster than less basic. Very robustness method and very high reproducibility obtained as well for migration time and peak area. We are also flexible with use capillary lengths, mentioned 30 centimeters, allowing us to be much more efficient with separation time. However, it might be not enough sufficient to determine eventual resolution of as well related with basic or acidic form. If more high resolution is needed, we can elongate separation capillary effective length, typically increasing double, means instead of 20 effective, we can use 40 effective capillary length. We can also modify buffer, which is provided in the kit. So on the next two slides, this and another one, I would like to present some work which was done and presented in one of SCIEX application notes related with factors affecting capillary electrophoresis separation of charged isoforms of nanobody samples, where we can modify 3-ethylenotetramine presence as a capillary wall modifier and how it's affecting for separation. In this case, was for nanobodies. We can also increase or decrease presence of commercially used in our kit hydroxypropylmethylcellulose, which increasing allows us to improve resolution between separated peaks. However, by absorptivity of HPMC, we can reduce eventual signal to noise obtained. Also, by different pH modification, means increasing or decreasing pH of the standard buffer, which original is approximately 5.7, we can affect for final protonation of separated proteins, knowing that we are able to protonate only proteins which are higher pI than used pH of buffer. Means we can protonate any proteins or peptides above pI 6. And this slide, also coming from the same tech note, showing comparison of three methods for tested intact and stressed nanobodies, which showing separation of capillary electrophoresis, ionic exchange chromatography, and isoelectrofocusing method. Summarizing all information, capillary isoelectrofocusing method provides highest level of separation of any of the conventional charge heterogeneity screening techniques and provides protein isoelectrofocusing point information not available from the other techniques like ion exchange chromatography or capillary electrophoresis. cIEF is a longer separation compared to other techniques and has been found to be robust under industrial ring trail conditions. However, capillary zone electrophoresis technique is much faster and increase high throughput of the method. Could be alternative to cIEF, and it's available as a commercial kit, easy to use and very fast separation. Both technique, isoelectrofocusing and capillary zone electrophoresis, can be further enhanced by multiplexing the separations on the new 8-capillary biophase 8800 system, something which is not available still for ion exchange chromatography.
Thank you for your attention.